Today we are going to discuss naive quasi-hyperbolic discounting. As you know that currently we are discussing intertemporal choice models, and under that first we discussed discounted utility model or exponential discounting, and then we discussed naive hyperbolic discounting. So, before I start discussing the alternative, that is naive quasi-hyperbolic discounting, I will begin with an example to show how the previous one that we have already learned, the naive hyperbolic discounting and exponential discounting, how do they differ? We will show it using an example, some numbers. So, suppose we assume that for all periods the consumption is equal to 200 and the utility generated by the amount of consumption is also equal to 200. This is a simplistic assumption. Beside that, if you remember, the discount factor for naive hyperbolic discount denoted by HT was 1 plus alpha t raised to the power minus beta upon alpha. So, we are assuming that alpha equals to 0.5, beta equals to 0.6, and in the exponential discounting model we had the discount factor delta. We are assuming two alternative values of delta at 0.8 and 0.6. After that, we are calculating the stream of utilities over a period of say 10 periods for alternative discount factors. So, this is first the hyperbolic discounting factor. When I have t equals to 0, then you can understand that 1 plus alpha t becomes equals to 1. When t equals to 1, then we have 1 plus alpha raised to the power minus beta upon alpha. For given values of beta and alpha, we have this value of ht. Similarly, when t equals to 2, then we have 1 plus alpha 2t, 1 plus alpha 2t, 1 plus 2 alpha raised to the power minus beta upon alpha, and then for values of alpha and beta which are already given, I can calculate a value of ht when t equals to 2. In a similar fashion, all these numbers are calculated. And then how do we arrive at the utility? It is simply 200, which is assumed to be constant, multiplied by the discount factor. So, when it is 200, 1 multiplied by 200 is 200, 200 multiplied by 0.603682 is this number, and so on. In a similar fashion, we have also calculated the utilities associated with the discounting factors, like when delta equals to 0.8 and delta equals to 0.6. We are calling them delta 1 and delta 2, just giving two names, and again multiplying delta by the discount factor multiplied by the utility is going to give me the stream of utilities and the stream of discount, future discounts, right. So, here you can see that when t equals to, how we discount under the exponential discounting, that is pretty simple. We have delta, then delta, it is delta raised to the power I for I taking any number. So, when I is equals to 0, we have 1. When I, that is time period, equals to 1, then we have delta equals to 0.8. T equals to 2, that is I equals to 2, then delta square gives us 0.64 and so on. In a similar fashion, I have for delta 2 equals to 0.6, then these discounting factors multiplied by the utilities which are constant at 200 gives us the stream of future utilities discounted to the present value. So, what these numbers as such do not show much, but if we plot them, then we can see how they are different. So, the red line is basically the exponential discounting with delta equals to 0.8. The green line is the exponential discounting with delta equals to 0.6, and in between lies the hyperbolic discounting. Now, what broadly it shows is that in case of exponential discounting, you can see the lines are smooth, in the sense here it is declining at a constant exponential rate. Similarly, this is also the case, but when it comes to hyperbolic discounter, then the initial drops are larger, after that the declines are much less as compared to exponential discounting with delta equals to 0.6. Now, the difference between having delta equals to 0.8 and 0.6 are mentioned here. When delta equals to 0.8, given that delta equals 1 plus r, or we can call it rho also. So, then the discount rate actually is much smaller. It is 0.25 when delta equals to 0.8 and 0.67 when delta equals to 0.6. So, when it is smaller, then we say that the discounter is actually very much patient. So, as a result of which you can see there is more equal spread of consumption over a large period of time, or the line is much smoother as compared to when the delta is a smaller one at 0.6, which implies that the discount rate is actually higher. And hyperbolic discounting actually lies in between the two. When it is beginning, this is merging with a high discount rate, which implies that this exponential hyperbolic discounter discount in the beginning much highly. Their discount rates in the beginning are much higher, but after that they reduce the discounting factor or discounting rate. As a result of time, over a period of time they actually converge with the exponential discounter having a lower discount rate. So, if you remember the example with Ted and Matthew, what Ted was doing, he was an exponential discounter discounting at a rate of 10% constantly, while Matthew initially discounted at a much higher rate of 30%, and then later on he was discounting it at 10% for the second period, and for the other periods, though other periods did not matter in that example, but then he was then discounting them at a 0%. So, if he starts discounting altogether after the second period, then the line becomes something like this. For all other periods, it is like constant, right. So, this is what this diagram basically explains the difference between exponential discounting and naive hyperbolic discounting. Next, we start talking about naive quasi-hyperbolic discounting. One of the primary advantages of the exponential discounting function is the simplicity with which the exponential discount could be used in solving maximization problem. So, basically the mathematical exposition has been much simpler as compared to hyperbolic discounting. By contrast, the hyperbolic discounting model can be difficult to deal with mathematically given the functional form for the discount factor. This has led David Leibson to propose an approximation to the hyperbolic discounting function called quasi-hyperbolic discounting. Quasi-hyperbolic discounting separates the hyperbolic profile of time discounting into two different discount factors. These two factors represent the discount applied to utility of consumption in the second period and the discount applied to the utility of consumption for each additional period. The discount factor applied to the second period is small relative to the other discount factor, representing the notion that people discount consumption tomorrow relative to today more heavily than the day after tomorrow relative to tomorrow. So, basically the initial time period discounting are much larger. In other words, any consumption in the future receives some penalty in the mind of the consumers, but trading of consumption between two different periods in the future does not face such a steep penalty. Thus, the model suggested is, this is again total utility from the current period to any number of periods C0, C1 to C2. That is consumption from current period to any number of periods. So, the first period utility is given by the consumption in the first period u C0. This is the current. So, we do not need to discount it, but from the second period onwards, two discount factors are introduced. One is beta, which remains constant for all future periods, you can see, and the second discount factor is delta, which keeps on getting its power basically keeps on increasing. So, in the first period it is delta raised to the power 1, second period delta raised to the power 2, third period delta raised to the power 3 and so on. Now, as you can see that for any value of delta less than 1, as we keep on increasing the power of delta, this number becomes smaller and smaller. That is additionally multiplied by one discount factor makes it even smaller. This is how I would say, rather, naive quasi-hyperbolic discounting. This is how I would say that the naive quasi-hyperbolic discounting provides an approximation to naive hyperbolic discounting, because as we said that in the immediate future the discount rates are higher as compared to as we proceed for later periods. So, from the first period to the second period, the discount rate actually is larger as compared to when we further keeps on moving, because then these multiplications multiplied by the constant discount factor make them actually very smaller, and the initial drop are actually larger, relatively larger. So, this can alternatively be written as u c naught I take it out plus the rest of them are summed up from I equals to 1 to t beta delta raised to the power I u c I. In equation 1, 0 less than beta less than delta less than 1. So, of course, we understand that most often delta is less than 1. We will also discuss possibilities of delta greater than 1, but much later, maybe towards the end of the next module. But more importantly, beta is less than delta, and if we want to consider the infinite time horizon problem, then t may be infinite. Here beta represents the discount applied to utility of consumption in the second period and in all future periods, and delta represents the discount applied to utility of consumption for each additional period as we move further into the future. In general, if beta is less than delta, the function approximates hyperbolic discounting. So, here in this figure, this actually refers to the exponential discounting. The triangles as mentioned here, marked in triangles, are quasi-hyperbolic discounting, and the squares are hyperbolic discounting. So, you can see that of course, quasi-hyperbolic discounting, as we have already mentioned, begins with a much larger increase in discount rate. So, the immediate future experiences a sharper drop, but exponential discounter actually represents a much smooth consumption spread over a period of time. Now, quasi-hyperbolic discounting actually is pretty close to the hyperbolic discounting. The advantage of this form is that it closely replicates the exponential mathematical form, thus restoring the simple mathematical formulas for time discounting problems. So, as you can see that quasi-hyperbolic discounting has, in terms of mathematical exposition, pretty a lot of similarities with exponential discounting, but as a result of which we have some advantage while dealing with mathematical exposition, but at the same time in terms of its structure it actually resembles the quasi-hyperbolic discounting. The solution to the utility maximization problem for equation 1 that we represented earlier again requires that discounting marginal utility should be equal in each period. However, the differential discount implies for I greater than 1, which is like u prime c I equals to beta delta raised to the power I u prime c I. Basically, for the first period or the current period you have u c naught, that is it. So, the marginal utility from the current period is u prime c naught. For the rest of the period, for I greater than equal to 1, you have this expression. Thus, given a functional form for the instantaneous utility function, we can find the relationship between planned consumption in one period and the next. For example, suppose that people must maximize the utility of consumption over an infinite time horizon given an initial endowment of wealth W. Suppose further that this is our utility function u c equals to c raised to the power alpha. So, that the marginal utility or slope of the utility function of consumption is given by u prime c equals to alpha c raised to the power alpha minus 1. Now, you can see that this utility function is actually not dependent on time as of now. So, u c represent any period where c raised to the power alpha is the functional form of the utility function. Then the optimization condition implies that optimization condition is like we equate the marginal utility from each period with each other. So, this is the very first period. Now, the current period also has an utility of c raised to the power alpha. As you can see that to begin with, you did not attach any time subscript to the functional form of utility. So, we have alpha c naught alpha raised to the power alpha minus 1. Basically, in this expression we are just putting the times in the subscripts, but for the next period onwards, that is from the second period onwards, I will be having two discount factors beta and delta. So, for the first period I have alpha beta, alpha is coming from here, beta delta remains as it is, C1 raised to the power alpha minus 1. For the second period, my discount factor is beta delta square. So, again alpha comes from here, then beta delta square, and then C2 alpha raised to the power alpha minus 1, and so on. So, this can be alternatively written as we simply multiply, or rather put a power of 1 upon 1 alpha minus 1. So, this cancels out and we are left with alpha raised to the power 1 upon alpha minus 1. Similarly, for all those components which did not have a power, they will be now having a power of 1 upon alpha minus 1. Those who had a power of alpha minus 1, the power would be gone. So, these are simple transformations. This implies that C1, that is the consumption in period 1, can be expressed as C naught beta delta raised to the power minus 1 upon alpha minus 1, and that in general. So, if we go for generalization of this expression, it is like the current period consumption multiplied by beta raised to the power minus 1 upon alpha minus 1, then delta raised to the power minus I upon alpha minus 1. So, here since it was for the first period, so beta delta both had the same power, but when you go for second period, third period, then delta will be having a slightly different power. Now, this is basically the first equation just represented here, so that we can match. The budget constraint implies that all consumptions spread over all the periods must add up to the total wealth one had begun with. Substituting from above, we have C naught. Basically, my consumption streams are like C naught plus C1 plus C2. So, C naught, then C1 would be plus this, C2 would be again, from this expression I can obtain the value of C2, which would be like C2 equals to C naught beta raised to the power minus 1 upon alpha minus 1 delta raised to the power minus 2 upon alpha minus 1. So, we keep on doing adding for each and every period, then we take C naught common out, and then we will be left with this expression that must add up to the right hand side, which is W. So, by applying the formula for sum of the infinite GP series, we can derive the closed form solution as this. So, this is the left hand side of the equation we showed in the last slide, and this is basically the infinite GP series which is summed up, and that formula applied. So, we have this thing 1 upon 1 minus delta raised to the power minus 1 upon alpha minus 1 is the sum of the infinite GP series. We have in the numerator beta raised to the power minus 1 upon alpha minus 1, everything multiplied by C naught, that equals to the right hand side, which is the total wealth. So, the idea is that all other periods consumption could then be calculated from the above formula. So, once I know the values of beta, alpha, delta and the initial consumption, I can actually calculate the consumption of all other periods 2, 3, 4, 5 up to infinity. This is one major advantage with the quasi-hyperbolic discounting over hyperbolic discounting, because in case of hyperbolic discounting, what happens is that suppose we model the same decision using a hyperbolic discount function, you would arrive at the following. So, in case of hyperbolic discounting, we will have this expression. Now, you can see that this is not a closed form solution, because here this is dependent on the time period. So, we cannot for each and every period we have to actually separately calculate. This cannot yield a closed form solution. So, that is what I was trying to tell you, that this is the advantage with using quasi-hyperbolic discounting over hyperbolic discounting. That is why the quasi-hyperbolic form is much more common in practice than the hyperbolic form, and in several books you would find that the quasi-hyperbolic discounting is referred to as the hyperbolic discounting, and there is no further mention of hyperbolic discounting. Thus, in many situations economists use the quasi-hyperbolic approximation rather than the hyperbolic form. In fact, the quasi-hyperbolic form is much more common in practice than the hyperbolic form that it approximates. Uri Benjian, Amon Rappaport and Joseph Yagel find evidence of changing discount rates over time. They asked 2,204 participants about their preferences between receiving bundles of money after various waiting periods. So, for example, one question asks participants to suppose they had just earned $200 for their labors, but after coming to pick up the money, they find their employer is temporarily out of funds. Instead, they are offered payment in 6 months. Participants were asked how much they would need to be paid at the later time to be indifferent between receiving $200 now or the higher amount later. The amounts of money and the length of time were varied. So, this is an example or the results from that experiment. So, basically they actually mentioned alternative amounts. The amounts are 40, 200, 1000 and 5000. The same situation, you want it now or you want it after a period. If you want after with a delay after some period, and those periods are like 6 months, 1 year, 2 years and 4 years, then how much more you would need? That was the question that were asked to them. The table displays the estimated discount factors for each of the various scenarios, similar to the scenario just described, assuming a money matrix utility function. And what we observe is that for all possible timelines, the initial discount rates are actually much higher, and after that they do not increase by substantial amount. After that the discount rates of course increases, but then the increases are more smooth. For each we see a relatively large discount factor for the first 6 months of delay. After that they become much smoother. So, discounts for longer periods are much smaller, reflecting the hyperbolic nature of discounting. If a person must delay a reward for some time, longer waits are no longer thought of as so costly. Similar experiments have been run with actual money payouts, finding additional evidence that discount factors climb over time, eventually becoming stable. Let us take an example. Suppose that you are on a diet, but have to decide whether to have a slice of red velvet cake at a party some random Saturday. Eating the cake could give you a utility of 4. If you have the cake, however, you will have to exercise for hours on Sunday, which would give you a utility of 0. We call this option C. The other option is to skip the cake, which would give you a utility of 1, and to spend Sunday relaxing in front of the television for a utility of 6. We call this option D. Thus, you are facing the choice between C and D. You discount the future hyperbolically, or rather quasi-hyperbolically, with beta equals to half and delta equals to 2 upon 3. So, the first question is that from the point of view of Friday, what is the utility of eating the cake and skipping it? Which would you prefer? So, I have two options. From Friday's perspective, option C, that I eat the cake and then do exercise on Sunday, is like beta delta, but because Saturday is tomorrow, today is Friday, beta delta multiplied by utility from eating the cake, then beta delta square, which is Sunday, the second day, that is why I have a delta square, utility from exercising on Sunday. So, Friday nothing is happening, so we assign a 0 utility, then beta delta multiplied by 4, the utility from eating the cake, beta delta square multiplied by 0, the disutility or utility from exercising on Sunday. These numbers were given in the previous slide. And what we observe is that given that beta equals to half and delta equals to 2 by 3, I have 4 by 3 utility from option C. Now talking about option D, I can skip the, or you can skip the cake and then relax on Sunday, again multiplied by tomorrow's discounting factor multiplied by day after tomorrow's discounting factor. So again for Friday we have a 0, then beta delta multiplied by 1, that is the utility from skipping the cake, plus beta delta square multiplied by 6, the utility from relaxing in front of television on Sunday, and that total amount turns out to be 5 by 3. So since 5 by 3 is greater than 4 by 3, you decide to skip the cake on Friday. So next, when Saturday arrives, the question is that from the point of view of Saturday, what is the utility of eating the cake and of skipping it? Which would you prefer? So when Saturday arrives, option C is eat the cake, and since it is Saturday, we do not have to discount it. This is the current period. Sunday will be discounted with a discounting factor beta multiplied by delta, and you exercise on Sunday. So eating the cake has a utility of 4. Then beta delta multiplied by 0, the utility from exercising on Sunday, your total utility is 4. Option D, you skip the cake multiplied by you beta delta plus beta delta multiplied by you relax on Sunday. So when you skip the cake, you get a utility of 1, beta delta multiplied by relaxing on Sunday, that is 6 units of utility, and this gives me a total utility of 3. Now 3 being less than 4, you decide to eat the cake. So what it shows is that the behavior here is time inconsistent. So this probably shows that the time inconsistent behavior is well explained by a model like quasi-hyperbolic discounting. Hyperbolic discounting is also able to capture it, but then we have already explained the advantages with quasi-hyperbolic discounting, and that is how time inconsistent or not so rational behavior from the perspective of neoclassicals, quasi-hyperbolic discounting model is able to explain certain preference reversals or time inconsistent behavior. With this, I conclude this model on the introduction of naive quasi-hyperbolic discounting. In the next, we will be discounting some of the behaviors that are neither explained by exponential discounting nor behavioral models of intertemporal choice. Thank you.